Whether you're baking a cake or you see a lizard warming up in the sun, our whole world is basically run by the speed of chemical reactions. But how do we actually measure that? Like, how do we understand the speed? Well, that's what we're going to get into. Let's unpack the science behind the speed of chemistry. All right, to get us started, I've got a little puzzle for you. So on one hand, you've got a lizard, right? Just chilling, soaking up the sun. And on the other, you have one of those high-tech medical test strips. I mean, they couldn't be more different, could they? But here's the thing. They share a really fundamental scientific principle. Any ideas what it could be? And the answer is speed. Yep, more specifically, the speed of all the chemical reactions happening inside them. Think about it. The lizard's metabolism, it actually speeds up as it gets warmer, which lets it move faster. And that test strip, its accuracy completely depends on reactions happening at a very specific rate. It really is all about the timing. Okay, so that brings us to the big question, right? When we talk about the speed or the rate of a reaction, what are we actually talking about? Let's break it down. The idea of a rate is something we're all super familiar with, even if we don't think about it. It's just a measure of how something changes over time. Your car's speed, for example, is just the rate of distance you cover per hour. Your wage? That's the rate of money you earn per hour. It's the exact same idea in chemistry. So when we bring that into chemistry, the rate of reaction is simply how quickly our starting ingredients, which, we call reactants, get used up, or on the flip side, how quickly the things we make, the products, are created. It's all about just tracking that change over a period of time. Okay, so that's the theory. But how do scientists actually measure this stuff in a lab? Let's jump into a real-world example to see how this all works in practice. So we're going to look at a really common chemical, hydrogen peroxide. Yeah, the same stuff you might have in your medicine cabinet. What's interesting is that it naturally breaks down or decomposes into plain old water and oxygen gas. And our goal is to figure out just how fast that happens. Okay, check this out. On this slide, you're seeing the actual data from the experiment. What scientists did was measure the concentration, that's basically just how much hydrogen peroxide was left, every 6 hours. And you can see it, right? That number just steadily drops over the full 24-hour period. That is our reaction, happening right there in the data. Now, to turn that raw data into a specific rate, we use this handy little formula called a rate expression. Now, I know it might look a little intense at first, but it's really just saying that the rate equals the change in the concentration of our hydrogen peroxide divided by the change in time. So let's just quickly decode those symbols so we're all on the same page. That triangle, that's the Greek letter delta, and in science and math, it just means change in. Easy. The square brackets you see, that's just chemistry shorthand for concentration of. And delta T, well, you can probably guess, change in time. See? Simple as that. But wait a second. Did you happen to spot that negative sign right at the front of the formula? Why in the world is that there? I mean, it seems a little weird to have a negative speed, doesn't it? Well, here's the really clever reason. Since the amount of our reactant is going down, it's decreasing, the change we calculate is technically a negative number. But by convention, scientists always talk about rates as positive values, just like we talk about speed. So that little minus sign out front, it's just there to flip the result and guarantee that our final rate is always a positive number. It's a neat little trick to keep things consistent. Okay, now here's where things get really interesting. You might assume that a reaction just, plows ahead at one steady speed, but that's not what happens at all. The rate actually changes as the reaction goes on. Just look at this. In those first 6 hours, the rate of decomposition was about 0.083. Pretty fast. But then look at the last 6 hours of the experiment. The rate has dropped all the way down to 0.010. So the reaction blasts off really fast and then it slows way down over time as those reactants get used up. A fantastic way to think about this is to imagine you're in a car approaching a stop sign. The initial rate, that's like your speed on the speedometer the exact moment you slam on the brakes. The instantaneous rate is your speed if you just glance down at the speedometer at any random point while you're slowing down. And the average rate? Well, that's what you'd figure out after you've completely stopped, by dividing the total distance you traveled by the total time it took you to stop. All right, so with all this new knowledge about different kinds of rates, let's circle all the way back to our opening puzzle. Let's figure out why understanding all this is so critical in the real world, especially when it comes to that medical test strip. So that little pad on the test strip, it is packed with something called enzymes. Now, think of enzymes as tiny biological catalysts. Their entire job is to make specific reactions happen, like incredibly fast. They're designed to react with something, say glucose in urine, and when they do, they produce a color. The speed of that color change is what tells the doctor exactly how much glucose is present. And this is why the instructions on those tests are so unbelievably strict. If you read the script too soon, say after 10 seconds, the main reaction haven't had enough time to produce enough color, and you get a false negative result. But if you wait too long, other, much slower reactions that are naturally in the urine can start to create extra color, giving you a false positive. The correct diagnosis literally hangs on measuring that instantaneous rate at the perfect moment. It's just like glancing at your car's speedometer at exactly the right second. But wait, there's one more amazing layer to all of this. In any given reaction, the speeds of all the different chemicals involved are actually connected. It's so cool. If you know how fast one thing is disappearing, you can calculate exactly how fast everything else is appearing. Let me show you how. Okay, let's use a new example for this. The decomposition of ammonia, or NH3, into nitrogen gas, N2, and hydrogen gas, H2. Now, pay close attention to the numbers out front. We start with 2 ammonia molecules, and they break down to form 1 nitrogen molecule and 3 hydrogen molecules.
Yeah, those big numbers out front in the chemical equation, those are the key. You can think of them like the ratio in a recipe, and the logic is actually really simple. The recipe here says, for every single nitrogen molecule you make, you have to make 3 hydrogen molecules at the exact same time. Their speeds are totally locked together in that 3-to-1 ratio. And chemists can capture that entire relationship in this one single elegant equation. I know it looks a little crazy, but all that's doing is using those recipe numbers, the coefficients, to link all the rates together. And this is the really powerful part. If you can measure the speed of just one single chemical in that whole reaction, this formula lets you instantly calculate the speed of all the others. You don't have to measure everything. You just need to measure one.
So you see, reaction rate isn't just some number you find in a textbook. It's the hidden timer that governs everything from biology to medicine to manufacturing. Understanding it means we know why a lizard needs the sun and why a doctor needs a stopwatch. Which leaves us with a pretty big question, right? Now that we understand the rules of chemical speed, what's the next great challenge we can solve by learning exactly when to hit the accelerator or when to hit the brakes?